we need to learn a little bit more about valence electrons. So far, the way we figured out how many valence electrons there are in an atom is by looking at their electron configuration. So oxygen's electron configuration is here, and we said that the valence electrons are the ones that are in the outermost energy level, so their highest energy level. And that's usually going to be the outermost S and P energy levels. So since oxygen's in the second row of the periodic table, that means the second row is the second energy level is the highest. So that means that these electrons are the valence electrons. So that means oxygen has 6 valence electrons. But it's a lot of work to do that, to figure it out, so we're going to learn a little shortcut. The first thing we should know is that elements in the same group have the same number of valence electrons. So that means elements that are in the same column of the periodic table all have the same amount of valence electrons. Let's see if there's another pattern we can pick up on. Let's look at only elements in the third row of the periodic table. So let's look at sodium, magnesium, aluminum, and silicon. If I were going to write out their electron configurations, I could start with neon as a noble gas as my abbreviated version, and I would come back around here, and for sodium I would have 3s1, magnesium would be 3s2, aluminum would be 3s2, 3p1, and silicon would be 3s2, 3p2. Let's use these to figure out our valence electrons. So sodium would have 1 valence electron, magnesium would have 2 valence electrons, aluminum would have 1, 2, 3 valence electrons, and silicon would have 1, 2, 3, 4 valence electrons. So if sodium has 1 valence electron, and we said that elements in the same group have the same number, that means all of these elements have 1 valence electron. Magnesium has 2 valence electrons, so that means all of these atoms have 2 valence electrons. The next one we looked at was aluminum, and we said aluminum had 3 valence electrons. And finally, silicon has 4. Do we see a pattern here? 1, 2, 3, 4. The next one would be 5, 6, 7, and finally 8 valence electrons. So from now on, if you want to know how many valence electrons an element has, just look at what group it's in, what column it's in. If it's over here, it's going to have 1. If it's in group 14, it's going to have 4. If it's in group 16, it's going to have 6. We are not going to worry about any of the transition metals, any of the elements in the D block. Don't worry, you're never going to have to worry about how many valence electrons they have. So we're just going to skip right over those. What we really need to talk about is how this relates to bonding. So let's use oxygen as an example again. So we said oxygen has 6 valence electrons. I drew an oxygen atom here. The valence electrons are the ones on the outside. We don't care about these 2 on the inside, just these 6. And remember the octet rule, which says that all atoms want to have 8 valence electrons. So if right now oxygen only has 6 and it wants 8, what is oxygen going to have to do to get to 8? It needs to gain 2 electrons. So if our oxygen atom gains 2 more electrons, it's not going to be neutral anymore. If it gains 2 electrons, it's going to become an anion, which means it's going to become negative. And since it gains 2, it's going to become a -2 ion. So what that means is oxygen atoms tend to get a -2 charge whenever they form compounds. And there's a special name for this kind of charge. It's called an oxidation state or an oxidation number. And all that word is just a fancy name for the charge that the atom will get when it obtains the octet. Let's look at fluorine as another example. Fluorine, we said, is in group 17, so that means he has 7 valence electrons. If it has 7, remember the magic number is 8. Fluorine wants to have 8 valence electrons. That means fluorine wants to gain 1 electron. And if fluorine gains an electron, fluorine is going to have a charge of -1. So fluorine's oxidation state or charge is just another word for that, would be -1. So let's see what this has to do with our trend on the periodic table. So we said oxygen wanted to gain 2 electrons, which made oxygen have a -2 charge. So remember, if all of the atoms in this group have 6 valence electrons, that means they're all going to want to gain 2 electrons. So they should all have a charge or oxidation state of -2. And fluorine, we said, was -1. So all of the atoms in that group should have a charge of -1. The 18th group over here already has 8 valence electrons. So that means they don't want to gain anything. So they're going to be all have a charge of 0. And our 15th group over here has 5 valence electrons. To get to 8, they're going to need to gain 3. So let's stop right there and move over to this side of the periodic table. So let's look at sodium as an example over here. So here's sodium's electron configuration. We said it has 1 valence electron. So you might think that since it has 1 valence electron, it wants to get to 8. You would think that sodium might want to gain 7 electrons. But that's not the case, and let me show you why. So here is sodium atom drawn out with all of its electrons. Remember, this right here is its only 1 valence electron. But if we look underneath that electron, there's a second energy level here, and that second energy level has 8 electrons. So sodium, instead of trying to pull in 7 more electrons, sodium's actually just going to take that 1 electron and give it away. And when it does that, picture this whole entire energy level on the outside disappearing. And when it does that, it has the second energy level, which has 8 as its outermost energy level, and it's happy. So sodium actually wants to lose 1 electron. And we know that if an atom loses an electron, it becomes a cation, which is a positive ion. So it's going to have a charge of +1. So that means all the atoms, all the elements in group 1 are going to get a charge of +1. Let's look at another example of magnesium. Magnesium's right next to sodium, has 2 valence electrons. Those are those right here. But instead of pulling in 6 more electrons, magnesium is going to just get rid of those 2 and then use these electrons on the inside as its happy 8 as to make its full octet. So instead of gaining 6, magnesium wants to lose 2. And if it loses 2, it's going to get a charge of +2. So all of the elements in the second group are going to get a charge of +2. So you can see this other pattern that's happening here. We have 0, -1, -2, -3 on this side. And over here we have +1, +2. Here we're going to have +3. So that brings us to this group in the middle, which has 4 valence electrons. Since it has 4, it takes kind of equal amount of energy to either give away 4 or gain 4 more. So the elements in this group are going to be plus or -4. So that is the reasoning behind the charges, or what we call oxidation states of the elements. Feel free to just memorize this pattern if that didn't make much sense to you. But either way, we need to be able to look at the periodic table and figure out what charge an element is going to get whenever it forms an ion. So in your notes, you can describe an oxidation number as the charge an atom obtains to complete its octet. And then you can show on this periodic table here what the oxidation numbers are. +1, +2, +3, plus or minus 4, -3, -2, -1, 0. Again, I didn't even include the D block or the transition metals because we're not going to worry about those.